Lesson 27 of industrial instrumentation. In this particular lesson, we will study basically the measurement of magnetic field. Basically, two sensors we will consider here. Though the title of the lesson is measurement of magnetic field, but you will find that especially the sensor, the second sensors which we had. So, we will study the measurement of current, measurement of power, all those things. But the first sensors that is the search coil is basically used for measurement of magnetic field, and second one is the Hall effect transducers that can be used for measurement of magnetic field as well as current. In fact, you will find that this particular sensors is extensively utilized, though it is name that it is used for the measurement of magnetic field, but you will find that it is extensively used for the measurement of current, especially high current, as well as the measurement of position or the proximity sensor, measurement of power, multiplications of the two signals. These all those things we will see that what are the different application areas of these Hall effect transducers. Let us look at the contents and all those things. Contents are search coil, magnetometer search coil we will basically discuss here. So, magnetometer search coil looks like this, that you have a, as we know that if a magnetic field, that if you move some coil anywhere, some voltage will be developed. So, using that principles that voltage will be measured and that voltage will be calibrated in terms of the magnetic field. Right. If the other things remains constant, obviously we will find that the output voltage will be directly proportional to the magnetic field. So, that is the search coil or magnetometer search coil. Sometimes people call magnetometer search coil, sometimes we call it simple search coil, right. And second transducers we will consider in details is the Hall effect transducers, right. Now, at the end of the lesson, the viewer will know the relation between various parameters like the magnetic field strength, flux density and the output voltage of the coil, total flux through the loop, etc., in case of magnetometer search coil, right. So, this thing basically we will know, and in the case of Hall effect transducers we will know the how parameters like flux density, dimension of the crystal, its Hall coefficient, current density, Hall voltage, etc., are related in case of Hall effect transducers, and how to use it to measure the current, flux density, power, etc., we will also study in this particular lesson. Now, magnetometer search coil is basic principle is something like this. A schematic of magnetometer search coil is shown in figure 1. A flat coil, okay, let us go back and see this one, then we will come back again here. You see, this is a coil which is, and it is placed under magnetic field, right, and its cross section area is A, length is L, and I am getting output voltage here E. Actually, this output voltage is to get some output voltage. Please note the two things is important, either the magnetic field must vary or this coil must change its position. Okay. There should be some movement of the coil. There is two option by which I will get a non-zero output voltage. One is that either H or B, if the H varies, because as you know B equal to mu H, H or B will vary, or the position of the coil will vary, then only I will get a non-zero output voltage. This output voltage can be calibrated in terms of the magnetic field. So, that is the basic principles of the magnetometer search coil. Let us go back to the previous slide, right. So, schematic of the magnetometer search coil is shown in figure 1, that is already we have shown, right. A flat coil with n turns is placed in the magnetic field as shown in figure, right. This is a flat coil, please note. Its coil can be two types, as you know. What is that flat coil? Please let us go back and see. The flat coil means like this. Yeah, You know, coil can be wound on a forma and it can have a shape like this one. Okay. It can usually before making inductance we make a coil like this one, right, and a coil can be like this one also. That means on a same plane I can have several turns, that means I can have several turns of the coil. If I look from the side, it will have just a several length of the wires and which is coming, right. So, it will look like this one. That is the reason we are calling it flat coil. There is some reasons why we are calling all this flat coil, because the dimensions of the coils is very important to properly predict the output voltage, if though we will calibrate the instrument, but that is very important. A flat coil with n number of turns is placed in a magnetic field as shown in the figure 1, right. N number of turns are there, it is a flat coil. Okay. Obviously, the more number of turns I will get more output voltage, that is also very important, but as you increase the number of turns, the size of the coil also will increase. No more the flatness whatever we are assuming, that will be valid, and moreover the weight of the coil also will be quite large. So, that creates other problems. The length of the coil is L and the cross sectional area is A, right. What is this cross sectional area? Let us again look at. I want to mean that suppose I have a coil of n turns. So, this filled up area I am talking of the cross sectional area A, right. This cross section area of the well, it is not the cross sectional of the wire by which I am making the coil, it is a cross sectional area of the coil itself. That means, if I just simply draw one simple loop like this one, right. So, I am talking of this cross section, this is our cross sectional area. Okay. This is the output voltage I will measure, right, which will be calibrated in terms of magnetic field. So, length of the coil is L and the cross section area is A. We will all talk about the SI unit A. So, this is all we talked about. Okay. There is a flux density connected to magnetic field H by mu, okay. And this is a cross section area A, this is the output voltage which is coming from the coil. The magnetic field strength H and magnetic flux density B are in the direction shown and are related by the following expressions. Okay, we have already shown the same direction it is working, you see magnetic field is also working in these directions, flux density is also obviously working the same directions, right. So, the magnetic field strength H and the magnetic flux density B are in the direction shown and are related by the following expressions: B equal to mu into H. What are these? Where B is the flux, magnetic flux density, which is in Weber per meter square, and H is the magnetic field strength which we want to measure, that is ampere per meter, right. We are interested to measure the magnetic field strength, and mu is the magnetic permeability for the free space, which is 4 pi, I am sorry, this will be 4 pi, this will be 4 pi into 10 to the power minus 7 Henry per meter, 4 pi 10 to the power minus 7 Henry per meter, right. So, the voltage output of the coil E is given by, now you see one thing is very important, you see here in the previous slide, we are interested in the measurements of H, right. Now, how much is the magnetic field actually? The value of B, this might be constant, this coming from some magnetic material, the value of H, depending on the medium, whatever the mediums which we are applying this magnetic field, I will get a value of B. Okay. So, B may vary depending on the particular medium, suppose water I have some different value of B, obviously mu will vary, in the free space we will have different value of B because mu will some other value. but H will remain constant for some specific application. So, we are more interested to measure the H rather than the measurement of flux density. Clear? The voltage output of the coil E is given by E equal to N A into cos alpha into d B by d t. Suddenly, why? How come this alpha came? Actually, we are assuming in the actual diagram, you see, if I go back to the diagram, I have shown it like that H is perpendicular to the plane of the flat coil, is not it? You see, the H is perpendicular to the plane of the flat coil, but that is not the fact. That may not be the fact, though it is always desirable that it should be perpendicular, then the output will be higher. If it comes in an angle, that means I am saying if it comes in an angle like this one. So, suppose I have a I am applying this magnetic field like this one. Suppose the magnetic field which is making an angle alpha, right. So, I am talking of that alpha, please note. Right. Again, I am reminding this is pi, not omega. The voltage output of the coil E is given by E equal to N into A into cos alpha into d B by d t. Okay. That means derivative of the flux density with respect to time. Now, obviously, it will be d H by d t because mu will come out, which is supposed to be constant for a medium, where A is the area of cross section of the coil, which is in meter square, obviously in SI unit, and alpha is the angle formed between the directions of the magnetic field and the line drawn perpendicular to the plane of the coil, just whatever I have shown. Okay. What is that? Exactly like this one, just I have shown. That means that I have a coil here, and though I could not draw it in a single plane, but we assume that it is in a single plane. Okay. So, this is the perpendicular to the plane. So, this is our alpha, clear, or this is our alpha. And alpha is the angle formed between the directions of the magnetic field and a line drawn perpendicular to the plane of the coil, clear. And N is the number of turns of the coil. As you increase the number of turns, obviously, the output voltage will increase, that I told you earlier also. If you A increase, because but the magnetometer surge coil is usually we are of the small dimensions, okay, because it is very easy to say that if you increase A, you will have the larger value of the output voltage, but if you think of a large A or keeping the shape of the that entire coil intact, having a large A and rotating it at high speed, it is not very easy task, right. The total flux through the loop, that means loop of the coil, is given by phi equal to A cos alpha into B, right. This is the total flux in the loop. So, that E equal to N d phi by dt, that means derivative of phi into dt, that is obviously always, is not, we have a voltage that will be N multiplied by d phi by dt, if it is in angle cos alpha, right. So, voltage output of the transducer is proportional to the rate of change of magnetic field. Okay, as you rotate it in a high speed, so that your output voltage also will, that means rate of change of flux will be directly proportional to the output voltage. Faster the rate of change of flux through the coil, that means faster rate if it rotates, I will get a larger output voltage. So, that is we are telling voltage output of the transducer is proportional to the rate of change of the magnetic field. If a stationary coil now is placed in a steady state magnetic field, that means a DC magnetic field, that means a field which is produced by a DC voltage, okay, or a permanent magnet, there will be no output voltage, because d phi by dt will be 0. So, there is no change of flux, okay, no variations of the flux with respect to time. So, the output voltage will be obviously 0. that we can see, because we have seen this part will be 0. Okay. So, output voltage will be 0. The search coil is thus a transducer that transforms a magnetic field signal into a voltage. That means, it converts that magnetic field into a voltage, which is can be easily transmitted, can be converted to the digital domain. So, all those things facilities are already there. It can be easily calibrated also if you have a standard magnetic field. In order to perform a measurement of a steady magnetic field, it is necessary to provide some movement of the search coil. Quite obviously, as I told you, if it is steady, that is the first bullet you see. If it is stationary, obviously, if it is stationary placed in a steady magnetic field, no output, I will not get any output, right. In order to perform a measurement of a steady magnetic field, it is necessary to provide some movement of the search coil, right. Some movement of the search coil will be necessary. So, I cannot change the magnetic field which I am going to measure. So, obviously, I have to make some movement of the coil. How? Let us look at how actually I am doing. A typical method is to use a rotating coil as shown in the figures with some motors. So, it will rotate at continuous speed. So, let us look at that. The RMS value of the output voltage for such a device will be given by ERMS 1 by root 2 NAB into omega. What are the other things? What are the legends? Where omega is the angular velocity of rotation, okay, of the coil. The figures I will show you. Let us go back to figure first, because it is very ridiculous. If I see, this is our coil. Okay, it is again flat coil. Okay, internal flat coils. Okay, so it is rotating by angular speed of omega. You see, angular axis of rotation. So, it is continuously rotating. So, I have placed this entire coil is placed in a magnetic field of H with a flux density B. So, coil is of length L. Okay, so, it will produce the output voltage, which will be measured at these two terminals. Which are those terminals? These terminals. I will get the output voltage E. Clear? So, this will be given the output voltage E. Let us go back. The search coil is thus a transducer that transforms a magnetic field signal into a voltage, and in order to perform a measurement of a steady magnetic field, it is necessary to provide some movement of the search coil. So, some movement of the search coil is necessary, that actually I am doing in the figure 2 as I have shown. Right. So, this is our coil. Now, there is some constraint here. Please note one thing, that the constant is that first of all, the coils should be of small size, and the dimensions of the coil should be very well known. Okay. The exact precise geometry of the coil should be known to predict the value of the output voltage. And as I told you, the smaller the size of the coil, obviously you will get the better results. That you must mention. I mean, it is worthy to mention that the size of the coil should be very small. So, this is the constraint, that the coil should be small enough and the magnetic field constant over its area, and this coil should move in a sufficiently high speed, right. This is another important thing to get a steady state value. Now, let us solve some problems, so that we will be more comfortable in the. So, the problem is a search coil has 10 turns and with a cross sectional area of 10 centimeter square. It rotates at a constant speed of 100 revolution per minute. The output voltage is 80 millivolt. Calculate the magnetic field strength. Let us take a white page. I will give a solution to this. So, this is solution to problem 27.1. Like this one, you see it is given that B equal to root 2 E RMS by N A omega. So, which will give you root 2 into 0.08 by 10, it is 10 centimeter square the cross sectional area, okay. Number of turns 10, right. So, it is in the centimeter square. So, it is to be converted in the meter square. So, 10 to the minus 4. So, you see this is the number of turns, right. This is the dimension. In the problem it is given 10 centimeter square, clear. So, I convert it in the meter into 100, because it is 100 multiplied by 2 pi by 60. So, which will give you 1.08 Weber per meter square. So, the H will be given by V by mu, which will be given by 1.08 divided by 4 pi into 10 to the minus 7, 10 to the minus 7 into 8.6 10 to the power 5 ampere per meter, right. This is the problem number, solution to the problem number 27.1, right. We have another problem. This is a problem 27.2. The problem is a magnetometer search coil has a nominal area of 1 centimeter square with 100 turns. The rotational speed is nominally at 180 rpm. Calculate the voltage output when the coil is placed in a magnetic field of 1 Weber per meter square. Please note this is not omega, this is W, right, and this will be simply W, or I should take, please note this is W, right, Weber per meter square. So, let us make the solution of this problem. So, again I am telling this is W. So, again you see the solution to problem 27.2. B equal to root 2 E RMS NAW E RMS equal to BNA omega by root 2. You see it is 1 then because it is 1 centimeter square. So, multiplied by 100 turns, right, into magnetic field is the, this is B is 1 Weber. So, it is 1, N is 100 into 1 converted into meter square 10 to the minus 4 multiplied by 180, excuse me, 2 pi by 60 divided by root 2. So, this will give you 1.27278 volts, right. So, this is a solution to the problem 27.2. right. So, we have solved two problems. Now, let us come to the more the other sensors, rather I should not say this is more important or that is less important. We have you see these even though it is very easy to tell that you rotate a magnetic coil, all those things, it is not very easy to do that, and it is the dimensions, everything is very very difficult to predict all those values. Okay. So, people what they do, because you have a much better sensors, much better devices, which is called the Hall effect transducers. It is actually developed by the one scientist, engineer I should say, name is Edwin Hall. So, the name also, the sensor is also given Hall effect. Actually, this effect he discovered while doing the other experiment, and the sensors later came on. So, the sensors also named under him, that means the Hall effect transducers or Hall effect sensor. Now, what is Hall effect? Let us look at. The Hall effect refers to the potential difference, which is we are calling Hall voltage, on opposite side of a thin sheet of conducting or semiconducting material in the form of Hall bar, through which electric current is flowing. A magnetic field is applied perpendicular to the Hall element. I will repeat it. Okay. I have a bar, looks like this one. If I take this one as a many times amplified or something like that, that means I will apply a magnetic field which is coming through this, going out this, right. I am applying a electric current which is entering through this and going out of this. That means I have applied some voltages, that is the reason that some current is flowing. If I apply a voltage magnetic field here, you will find that across these two surfaces, this and this, a potential will be developed. That potential is actually, we are calling it a Hall coefficient, right, Hall voltage rather. So, the Hall effect refers to the potential difference or Hall voltage on opposite side of a thin sheet of conducting or semiconducting material in the form of a Hall bar, through which electric current is flowing and a magnetic field applied perpendicular to the Hall element. The ratio of the voltage created to the amount of current is known as the Hall resistance, and the characteristics of the material of the, and this is the characteristics of the material of the transducers, and the Hall effect sensors is shown in figure 3. Let us look at Hall effect transducers. This is our Hall effect transducer, is a thin metal plate, okay, of thickness T. So, I applied a voltage V, a potential V, okay, and you see this is basically a Lorentz Lorentz effect will come. In fact, some people say that the current carrying that the current actually carried by the electrons, actually that was first proved by the Hall, Edwin Hall, right. So, I am applying a potential here through a battery. You see the current is flowing through this one, and some voltage will be developed across this. That is I have shown like this one. Clear? Very clear. I will look at this one, same thing. Okay. I am applying a magnetic field here. Okay. That means I am applying magnetic field here. Okay. A current is flowing through this one. Applying a current, it is coming and it is going out through this. Right. So, Hall potentials. If you take these two terminals, your voltage will be developed. That voltage is called as a Hall voltage. Clear again? Right. So, it should be sufficiently thin. A semiconductor plate, actually you will find that the Hall coefficients or Hall voltage is more predominant in the case of semiconductor, though in all metals supposed to have some Hall voltage, but you will find in the case of semiconductor this is more predominant. A semiconductor plate of thickness T is connected as shown, so that an external current I passes through the material, okay, due to some battery voltage. And when a magnetic field is impressed on the plate in a direction perpendicular to the surface of the plate, okay, there will be a potential EH, that means the Hall voltage E subscript is generated as shown, and this potential is called the Hall voltage and is given by EH equal to KH into I into B by T. Okay, this is our expressions of the Hall voltage, right. So, a semiconductor plate, as I told you, it will have a larger value of the Hall voltages. Hall voltage of thickness T is connected as shown, so that an external current I passes through the material. When a magnetic field is impressed on the plate in a direction perpendicular to the surface of the plate, there will be a potential E H generated as shown, and this potential is called the Hall voltage and is given by K E H equal to K H I V divided by T. Clear? The legends are I is in amperes, B is in Gauss and T is in centimeters, right. The proportionality constant is called the Hall coefficient and has the units of volt centimeter per ampere Gauss, right. So, it is a Hall coefficient and is a characteristics of the particular material, okay, and has the units of the volt centimeters per ampere Gauss. Hall effect device produce very low signal level, so that it is to be amplified. So, it needs some amplifications because the voltage is very small. Please note, it is not a very large voltage. So, a good amplifier, low noise amplifier is necessary, though the voltage is DC. So, that simplifies a lot of problem, right. Hall effect sensors are in fact a device containing both the sensors described and a high gain IC amplifier in a single package. Okay, nowadays these are made I think in thousands and thousands because of the Hall effect transducers. We can see that if I know the if I can predict that EH, I can measure the current also, is not it. If I know the potential, okay, let us go back a little more clear. You see here, if I know the KH of the material, if I know the B, if I know the know the EH, if I can measure the EH, this EH can be calibrated in terms of I, is not it, if the I is unknown. So, by measuring EH I can tell the I, clear, because this is the only thing variable. So, Hall effect sensors, that is the reason Hall effect sensors are extensively used for measurement of current, large current, very large current around 500 amperes and all those things. There are various type of Hall effect sensors are also used. And moreover, suppose if this I is constant, if I can vary B, I can use this Hall effect voltage EH to use it for proximity sensor. Clear? How? Let us look at. Hall effect sensors in fact a device containing both the sensor and described and a high gain IC amplifier in a single package. Advantage of the Hall effect sensor. Hall effect devices, when appropriately packaged, are immune to dust, dirt, mud and water. Okay. In many places, I mean hostile environments, I may use this. Okay. It does not depend on how much dirty it is, it will work same, right. Calibration, I do not have to recalibrate the instrument, that is the great advantage of the. So, Hall effect devices, when appropriately packaged, are immune to dust, dirt, mud and water. So, any that type of environments I can use this Hall effect sensor, especially for the measurement of current. Okay. That is, it is most extensively nowadays not for the used, not for the measurement of magnetic field, though when we have started this lesson I said that the measurement of we are discussing the measurement of magnetic field, but please note this since it is Hall effect transducers, we are actually discussing historically actually the Hall effect transducers are used for measurement of magnetic field, but it is nowadays extensively used for measurement of current. Excuse me. These characteristics make Hall effect devices superior for position sensing. This is another important, or proximity sensing that I told you, compared to alternative means such as optical and electromechanical sensing. Okay, electromechanical sensing does not work in the dirt, as you know, because dust will always block the passage of light. So, this optical system also does not work for a very small change. Okay. So, I can use this Hall effect. We will show that how it actually works. Hall effect current sensors. This is a current sensor based on Hall effect. You see here a current. I want to measure this current which is flowing through this wire. This is a section of the wire which I have shown. Section of the wire. You see, this is a section of the wire. Okay. it is placed under a magnetic field, a ferrite core. This is our Hall sensors, right, and I am sending a constant current through this. Okay, current is entering here, current is coming out of this. You see, current is coming through the here and going through this and coming out through this one, right. I am measuring the output voltage across these two terminals, this terminal and this terminal, the output voltage. Okay, let me take another color. So I think this is not very clear. This color and this I am measuring the voltage, right. Now what will happen? You see that this, since it is a ferrite core, so amount of magnetic field also will depends on the current which is passing through this one. As we have shown that this EH, the output voltage or Hall voltage, depends on the magnetic flux density, and this flux density will depend on the sense current, which is the current which is flowing through the wire, right, along with in conjunction with the ferrite core. So that will give you different value of B for different value of the current, right. So accordingly what will happen, this output voltage will vary. So this output voltage will be calibrated in terms of the sensed current. This is the basic principles of our Hall effect current sensor. Clear? If current of both AC and DC are to be measured, sensor based on the Hall effect or the magnetic resistance, magnetoresistance effect can be used, right. In a typical open loop sensor, the current carrying conductor is passed through the hole in a gapped ferrite core used to concentrate the magnetic field. Okay, that is we have shown. Is a gapped ferrite core. What is the gap? You see, it is not continuous. It is, there is a gap. After this, there is a here. Okay, so there is a gap. So inside that gap, we put this one. Why this gap? To concentrate this magnetic field, and this magnetic field depends on the current which is flowing, right. It does not depend on the ferrite core only, depends on the current which is flowing through the line, right. So that means B. So the B will change due to if the current changes, so the output voltage will change. So output will be calibrated in terms of sense current. So in a typical open loop sensor, the current carrying conductor, because it is open loop sensors, because in some Hall effect sensors are used in closed loop control also. So that is the reason we are using the term two different open loop and closed loop. In a typical open loop sensor, the current carrying conductor is passed through the hole in a gapped ferrite core used to concentrate the magnetic field, and the Hall device is in the gap. As we know, the Hall sensor is a magnetosensitive semiconductor that provides an output voltage proportional to the product of its current, which held constant, and the component of the magnetic field that is perpendicular to its surface. We have seen previously, this is so many times, right. The Hall sensor is a magnetosensitive semiconductor that provides an output voltage proportional to the product of the current, which is held constant. Okay. So if I use the battery voltage constant, so it will remain constant, and the component of the magnetic field that is perpendicular to its surface, right. Since this field is proportional to the current being measured, that I told you several times, twice, the device output voltage is proportional to the sensed current. This is the most important, this second point, right. What is that? Since this field is proportional to the current being measured, right, field will depends on the current, and the device output voltage is proportional to the sensed current. So using these principles, we are making this Hall effect current sensors, as simple as that. A typical device has a range of, as I told you, 0 to 350 ampere, and the frequency response from DC to 1000 Hz. Hall effect current sensors is like this one. What is this DC I am talking about? Suddenly, typical device has a range of 0 to 350 ampere, that is understandable. It can measure a current of 350 ampere, and please note it is a non-invasive device, non-contact device. If you want to measure, I do not have to put an ammeter, I do not have to cut the wire, right. That is a great advantage. Any meter measurement of current will be, I mean, is necessary. Okay. We had previously the CT, PT and all those things, current transformer, potential transformer, a little obsolete, that type of instrument. So, I can use the Hall effect transducers there, clear. Totally you do not have to cut the wire to measure, because whenever you want to measure a current in the wire, you have to break the wire and connect an ammeter, but which is not necessary here, right. So, when the online, that means when the circuit is working, okay, fine, you can bring a Hall effect transducer setup like which I have described and measure the current which is passing through the coil. Frequency response of 0 to 1000 hertz. What is this suddenly frequency response? That means, can I measure AC current here? Yes, why not? The output voltage which you will get, that will also will be AC, but the magnetic field remains constant, that is DC. No, that also will vary. Obviously, if this is AC, that B will also vary. So, the output voltage will also be AC. Hall effect current sensors, the magnetic field may be that provided as a consequence of electrons flowing through a conductor. So, this is as I told you earlier, because this Hall effect, Hall voltage actually developed due to the flow of electron in the semiconductor, in the conductor or in the metal or in the semiconductors. So, some people say that actually in the metal, that it's the current flowing through the metal is due to electron was first established by the Edwin Hall. Magnetic field may be that provided as a consequence on electron flowing through a conductor. It is thus possible to create a non-conducting current sensor, which I told you some time back, in which the conducting cable with current to be measured is threaded through a hole in the sensing devices. Okay, just through a hole in the sensing device. We will show you such a devices, that more clear to you. The device has 3 terminals. Let us look at, this is our current sensors. Okay. You see the wire through, I mean, which will be in which you are interested to measure the current will pass through this. Please note, the wire will pass through this one. So, it will go out like this one, clear. So, this should pass through this one. So, this is a compact systems, our current sensor, right. Hall effect current sensors with internal integrated circuit amplifier. This is total 8 millimeter opening. Zero current output voltage is midway between the supply voltage that maintain at 4 to 8 volt differential. Okay. Non-zero current response is proportional to the voltage supplied and is linear to 60 ampere for this particular, which is 25 ampere device. Across 2 of these is applied a sensor voltage, okay, because I have to give a voltage, is not it. Okay. And from the third is taken a voltage proportional to the current being measured, right. So, across the 2 of these applied a sensor voltage, which actually will give you the current I, capital I. You remember our basic expressions. Okay. What is that? Let us look at. When I am telling that, you see here, kH IB into mu by T. So, this I is remaining constant. Okay. Across the 2 of these applied a sensor voltage. So, sensor voltage will make this I constant, kH, B, T, everything remains same. So, I will measure EH, will measure the current. So, current also will vary the B actually. These have several advantages. So, no resistance or shunt needed, because you see the typical measurement of current, large current like 500 amperes, I mean 6 and 1000 amperes, we are using a shunt. What is that? Shunt is basic principles, all of you know from your first year classes. I have an ammeter which can measure, suppose I have an ammeter. Suppose it can measure only 0 to 1 ampere, but I want to measure a 100 ampere. So, what I will do? I will put a shunt, a low resistance across this one, R shunt. Okay. So, large current will pass through. So, this RH is much smaller than the resistance of the ammeter, Rm. So, the large current, most of the current, if I want to measure, now we want to change it to 100 ampere. So, most of the current will pass through shunt and small current will pass through this. Okay. Again the same problem, this shunt and all the business, that is not necessary in this particular case, right. So, these are the several advantages. So, no resistance, a shunt need to be inserted in the primary circuit, and also the voltage present on the line to be sensed is not transmitted to the sensor, and a characteristics which enhance the safety of the measuring equipment, that is most important thing. You see what I am saying. Also the voltage present on the line to be sensed is not transmitted to the sensor. So, the whatever the voltage, because I am measuring the current, so that will be associated with the large voltage might be. So, that voltage will not come to EH, because EH whatever we are talking about, that will be this voltage. What I am saying, that you see this EH, this EH KH IB by T. B is changing, getting changed due to the sensed current. This sensed current might be associated with large voltage, okay, fatal voltage might be order of kilovolt, but that voltage is no way connected here. It is not coming to the measured, output voltage of the sensor, because that will give you some value of the B. So, as the I changes, that means as the current which I am sensing, that is changing. Please do not confuse this with the I, this I with the actually the current we are measuring. This current, this small I, this I is actually the current, a DC current which is established in the Hall sensor by a steady voltage. Okay, that is a very small voltage. Okay. We are not measuring this current I, we are measuring a current, okay, which is changing the value of B, right, and we are measuring the EH. So, that might be associated with large voltage, fatal voltage, but that will not come to the picture. That is what is, that will not come to the sensed output. That means, the terminal which we are using for measurement of that voltage, the Hall voltage, is no way getting that high fatal voltage, is not it, because dangerous voltage, high tension voltage. So, that is no way connected, because it is no way totally non-contact sort of devices. There is no physical connection between the current which I am going to sense or going to measure and the output voltage, right, no mechanical connection, nothing else. The range of the current sensor. The range of a given fit through sensors may be extended upward and downward by appropriate wiring. So, by you can wiring, that means I can make it larger and smaller. Okay. To extend the range to lower currents, multiple turns of the current carrying wire may be made through the opening. Okay. That because there is an opening through which the current sensors will go. To extend the range or to the higher currents, a current divider may be used with a portion of the current carried by a large wire flowing through a smaller parallel wire with a thicker wire passing to the sensor. There is the same principles of shunt, but it is not very popular in that sense. That means, I have to take some other, that same shunt business I am introducing again. So, I should not say it is very popular. Usually, typically you see the Hall sensors are used for as a typical range. The same Hall sensors which are used for measurement of current of 100 ampere, you are not using that Hall sensor for measurement of 1000 ampere. For 1000 ampere, you must have some different, altogether different sensor assembly. We can have a split ring clamp on current sensors also. Okay. A variations on the ring sensor uses split sensor, which is clamped onto the line rather than the threading the line through the sensor, enabling the devices to be included in the test equipment, and it is not permanently installed in the device being tested. Excuse me. This also simplifies the permanent addition of current sensing to existing circuit, as they need not to be dismantled to perform the installation. So, okay, you do not have to dismantle the thing, right. This is one way, though it is we are using a clamp on sensor, this is one way it is good, because you do not have to dismantle the entire system. Now, analog multiplications, because you see you will be surprised suddenly how come we have come to the analog multiplication we are talking about. You see, the analog multiplications is a we are talking about, because though it is a signals, I cannot, two signals can multiply. We are so far talking about this excuse me, suddenly how it came the analog multiplication business. Let us look at the output is proportional to the both the applied magnetic field and the applied sensor voltage, right. The output is proportional to the both the applied magnetic field, applied sensor voltage, is not it. You see, the applied sensor voltage what is? Let us go back again. Sorry. Okay, let us again we are telling that we are writing EH, KH into IB into T, right. If KH is constant, T is constant. Okay. So, output voltage EH, I can say that output voltage EH is proportional to I multiplied by B, is not it? That I can tell quite obviously, if KH and T are constant. But the thing is that you see that how I am saying that these two signals will be multiplied. What is B again? B will depend on the magnetic field. Now, if I can make B which is proportional to some other current, because I will depend on the current which is flowing through the sensor. B will, if I make the B proportional to some current, so obviously I can say that the output voltage will be multiplied, output voltage will be proportional to the multiplications of the two currents, is not it? That is exactly what we are doing in analog multiplication. Let us look at. Now, let us go back again. Output voltage, output is proportional to both the applied magnetic field and the applied sensor voltage, right. If magnetic field is applied by solenoid, then the sensor output is proportional to the product of the current through the solenoid and the sensor voltage, is not it? Okay. So, using that principles I am making the analog multiplication. Power sensing, by sensing the current provided to a load and using the device applied voltage as a sensor voltage, it is possible to determine the power flowing through the device, right. This power is for direct current devices, the product of the current and the voltage. With appropriate refinement, and the devices may be applied to the alternating current applications, where they are capable of reading the true power produced or consumed by a device. Position and motion sensing, that is most important thing, which is when it is applied to the mechanical motion sensing and the motion limit switches, the Hall effect device can offer enhanced reliability in the extreme environment. As there are no moving parts involved within the sensor or magnet, there is a far greater useful life expected than from the electromechanical switches, right. So, again the position sensing is possible. That means, if I by some means by changing the position, I can change the value of B, capital B. Okay. The capital B we have written so many times. So, the obviously the output voltage will be proportional to the B. So, I can sense the position. So, the position sensor, we can make position sensor using this principle, this whole principle. The sensor and the magnet may be permanently and completely encapsulated in an appropriate material. Now, let us look at the problem, last problem 27.3. Let us read it. It is a germanium crystals having a dimension of 6 into 6 into 3 millimeter is used for the measurement of flux density using Hall effect sensor. When the Hall field and the Lorentz force balance each other, it is observed that the current density in the crystals is 0.3 ampere per millimeter square, and the Hall voltage developed is minus 0.35 volt. We have to find the value of the flux density and the velocity of the electrons in the Hall sensor itself, right. Now, suddenly you can see that how we have introduced the Lorentz force. Lorentz force is basically a force which will try to oppose, the basic accumulation of the charges, okay, on the two extreme side of the plate. We have seen that, we have told several times that you see that when we apply some voltages, okay, on the opposite surface of the plates, a voltage will be developed. Why this voltage is developed? This voltage is developed because there is a accumulation of the charges. Now, Lorentz force is basically when this Hall effect and the Lorentz force will balance each other, we will get a steady output voltage E h, right, whatever the small time might be 10 to the minus 14 seconds, but within this short time there is a balance will be achieved. Is it clear? That is why I am saying that when I applied it in a Hall effect transducer, when I applied a voltage, okay, which will give me a steady current I, okay, and it is under the steady magnetic field B, okay, what will happen that there will be the redistributions of the charges or the electrons inside the Hall two sides of the plates, and the Lorentz force will balance that thing, and due to these accumulations of the electrons, I am getting a definite non-zero voltage, which is we are calling it Hall voltage, right. Let us look at that problem again. This is our problem. So, given Hall coefficient for the germanium crystal is minus 8 into 10 to the minus 3 volt meter ampere Weber per meter square. Solution C H equal to kh B I by T, we have seen. So, B equal to kh T by kh by into I. So, this you just put all this value of B. Okay. So, B equal to 0.012 Weber per meter square. So, now when the Hall field and Lorentz force must balance. So, I can write it is the movement of the velocity B is the velocity of the electrons inside the Hall sensors. So, E B h by B. So, B equal to E h by B by small b. Let me go. Yes. So, which will give you the speed of the electrons as 972. These are all the dimensions of the Hall plates. B is the dimension of the Hall plates, 9722 meter per second, right. With this, I come to the end of the lesson 27 of industrial instrumentation.